This is the first lesson in our unit about gases. We're going to start off this unit with a quick review about kinetic energy, phase changes, and states of matter. That information may be familiar to you, but even if it is, I think it'll still be a useful review. Then we're going to talk about a theory with a really scary name, the kinetic molecular theory of gases, which is a lot scarier than it sounds, and it gives us some rules for how we can think about gases. And finally, we'll look at a few unique properties of gases that are very different from those of solids or liquids. So let's take a look at kinetic energy first of all. Kinetic energy is a type of energy that anything has if it's moving. So a Mack truck, if it's barreling down the highway, it has kinetic energy, and even a tiny little atom moving around has kinetic energy. The thing about kinetic energy is the faster something's moving, the more kinetic energy it has. So a kid sprinting down the street has more kinetic energy than that same kid just walking down the street. Likewise, an atom that's moving really fast has more kinetic energy than that same atom that's moving very slowly. The idea of kinetic energy is particularly important when we start talking about phases of matter. Let's take a quick review, brushing up on what we probably already know about phases of matter. I have here indicated some certain representations of phases of matter. I have a container and some particles in it. I've got a representation of a solid, a liquid, and a gas. Let's start with a solid. A solid here, like all the other phases of matter, is made up of particles. That's what these little red circles represent. Particles can be either atoms or they can be molecules that are formed by the atoms coming together. Either way, all matter and all things are made up of particles. So in a solid, the particles, as you can see, are packed together really tightly. They have very little kinetic energy. They're moving around a little bit, but for the most part, they're locked in place and they're locked to their neighbors. The particles in liquid have more kinetic energy. They're moving around and they're freer to move. They're still locked in with their neighbors to some degree, but they're swimming around. They're swimming in close proximity to the particles nearby. Gases, on the other hand, have a ton of kinetic energy. In fact, to make this picture even more accurate, what I'm going to do is I'm going to add a few arrows. These arrows are going to represent the fact that these gas particles are in constant motion. They're moving around all over the place. They're banging against each other and they're banging against the sides of the container that they're in. In fact, these gas particles are moving so quickly that at room temperature, they have about an average speed of 1,000 miles an hour. That's just how fast they're zipping around here in this container. So solid, liquid, and gas have increasing amounts of kinetic energy. Gases have the most kinetic energy. They're flying around in there, and they're not connected at all to their neighbors. Now, this is a very superficial representation of what a gas looks like, but often we're going to want to look at problems and think about gas conceptually in a way that will make it necessary to have some deeper understanding about what a gas is and how these gas particles behave. We obviously can't see gas, so in the problems that we're going to do later on, we have to have a way to think about it, a way to conceptualize it. So it's useful to set up a series of rules for how we expect gases to behave. We'll make these rules or assumptions, and then we can keep them in mind when we have to solve problems or do calculations. Now, this list of rules is what's called the kinetic molecular theory of gases. Oftentimes it's just referred to as the kinetic theory of gases. And as I said, it's a list of rules, expectations, assumptions of how we expect gases to behave. Now, if a gas follows every single one of these rules, we call it an ideal gas. But in the real world, it's very hard to come up with an example of anything that always follows all the rules. We might want to think that there exists some things like a perfect student, an ideal student, or an ideal kid, but rarely that's the case. Almost always we find a few exceptions to the rules. And so because of that, it's helpful to think of an ideal gas, but in the real world, none of these gases that we're going to talk about ever follow all the rules all the time. At the end of this unit, we'll look at some particularly bad offenders, gases which break rules more often than others do, and we'll look at certain situations that cause gases to break the rules. For the most part, though, in all the gases that we're going to look at now, we're going to assume that they're ideal gases. We're going to assume that they follow all the rules all the time, and for the most part, most of these gases only break the rules in little bits once in a while. So we can safely assume that all the gases we're dealing with follow these rules of the kinetic molecular theory. So let's take a look at what some of the rules of this are. And once again, sometimes it's just referred to as a kinetic theory. I'm going to write down here, kinetic molecular theory of gases. So in no particular order, let's take a look at some of the assumptions that we make about gases. Oh, here's the first one. Gases consist of very small particles that are far apart relative to their size. This is something that's very difficult to depict visually, and I certainly didn't do a good job of it in the phase diagrams that I just showed you. Gas particles in the picture that I drew you look like they're the size of marbles in a glass jar. This isn't true at all. Gas particles are so tiny that instead of thinking of them as marbles in a glass jar, if the gas particles are the size of marbles, our container would be like the size of a football stadium. So these guys are absolutely tiny, and there's a ton of empty space between them. That's the first thing that we want to keep in mind when we're dealing with gases. Here is a second thing, and this is very important. Gas particles are in constant random motion. We hinted about this earlier with those arrows that I drew of the gases moving around. The moving particles constantly collide with each other and with the walls of the container. So all the time, whenever I have gas in any sort of a container, or even if it's just in a room, these guys are zipping around, they're bouncing against the walls, and they're bouncing against each other. Now, let's think about those bounces a little bit more. There are a variety of ways for things to bounce into each other. And here we say that collisions between gas particles and container walls are elastic collisions. What's an elastic collision? Let's think about two balls of slime. These two balls of slime on either side of me come together, and what's going to happen? They're just going to hit each other and they go, bleh. This is what we call an inelastic collision. That means that the kinetic energy that both of these guys had got wasted in the collision. These guys were both moving, they came together, and they just kind of went blah. And all the kinetic energy, the speed, the motion that they had disappears in the collision. This is like what happens if you chuck an egg against the side of a wall. It hits the wall, and then it just drips down, but the motion that it had, the kinetic energy disappears. That's an inelastic collision. The collision between gas particles and container walls, on the other hand, are elastic collisions. A good way to think about an elastic collision is think about what happens when two red or pink round rubber balls hit each other. They hit and they bounce right off. Or one of those pink rubber balls hits the side of a wall, bam, it bounces right back. The kinetic energy isn't wasted in the collision. So this ball hits here and it has the same amount of kinetic energy afterwards that it had when it started. That's the exact kind of collision that gas particles get into. They bang into each other and they just fly right apart, or they hit the side of a container wall and they just bounce right off it. So whenever you think about gas particles colliding, you always want to keep in mind the idea of elastic collisions. Additionally, we can say that there are no forces of attraction or repulsion between gas particles. Some particles, like water molecules, kind of like each other, and so almost like weak little magnets, they tend to attract. Other particles, two particles that have the same charge, don't like each other. They're sort of afraid of each other, and so they're going to repel. They don't want to get anywhere near each other. What this law is saying, when we say there are no forces of attraction or repulsion between gas particles, what we mean is that the gases are flying around and they're not going to start clumping together because they're attracted to each other. That doesn't happen. There's not that attraction. Likewise, let's assume that two gas particles are passing each other. They're just going to fly right by. If they repelled each other, zoom, they'd hit out that way when they get close. That doesn't happen. They don't repel each other and they don't attract each other either. Lastly, here's what I think is probably the most important thing to keep in mind when we're talking about the kinetic theory of gases, and that's that the average kinetic energy of gas particles depends on the temperature of the gas. The hotter it is, the faster they move. So remember that. Hotter for gas movement equals faster. This is tremendously important. The hotter it is, the faster these gas particles move around. So in this kinetic theory of gases, we've looked at a few of the rules that we always want to keep in mind whenever we're dealing with gases. And again, we're going to assume that all the gases we're dealing with follow these 5 rules that we just talked about.